It is going, well, the goal is not to watch it, but to blow stuff up. Let's try reloading it. Because there's not a good YAPC if there isn't mischief.
It's going to have black at the beginning.
Yeah. All right, well, we'll get started and revisit it towards the end and see if that works. All right, hello everybody. My name is Mike Friedman. This is the Perl API for the mortally terrified. I named it that because, well, the goal is not to watch it, but to blow stuff up. It worked. I blew it up. All right, I'm going to quit that now. That surprised me. I had no idea what was going on for a second. All right. So I named it Perl API for the mortally terrified because I had to learn this stuff for my job, and I was scared of it. I had been hacking Perl since about 2000, maybe even a little earlier than that. And I had done some CPAN releases. I thought all corners of Perl, but I never really done any XS stuff. But then I had to learn it, and I had to figure it out. So my name is Mike Friedman. This is me. I work for MongoDB. MongoDB are the makers of a really fantastic open source database. You might have seen me just talk about it in that room over there. We are hiring engineers, so if you have really excellent C++ skills or Golang skills or Python skills or Perl skills and you want to work on something cool in New York City or Palo Alto or perhaps elsewhere, come bug me and I'll give you a card and we'll talk about it. So this talk is the product of a lengthy journey. I started working for MongoDB about 2 years ago, a little less. And initially my job there was to maintain the Perl driver for MongoDB. And that's since been taken over by somebody else. I'm now working on some other top secret stuff. But when I applied for the job, I saw there's this great Perl job, work with MongoDB. They specifically wanted me, in addition to doing that, to work with the Perl community as well. So I said, this sounds really nice. And then I saw on the job it said, you have to be familiar with C and XS because the Perl driver, a big chunk of it is written in C. So I said, well, how do I deal with this? And I wrote a cover letter that said, I have some limited experience working with Perl and XS. And what that actually means is I had no experience. But amazingly, my other qualities seemed to make up for that, and I got the job. So the moral of the story is, always exaggerate on your resume. So in order to do this, in order to then do this job, I then had to learn this stuff. I'd kind of take a crash course in it. And I knew, C as a language, but I didn't really know XS or the Perl API. So let's figure out what we can actually do with this. The main reason, the main motivation people want to use this is to make things fast. You can take your Perl code and write it in C. So if you have a particular Perl function that's slow, you want to make it fast, you can write it in C. But the nice thing about this, instead of just, you might say, why not just write a C program? Well, the reason is because you can keep your other Perl code, the stuff that doesn't need to be optimized, in Perl, which optimizes programmer efficiency because it's much faster to write stuff in Perl than it is to write in C, even if you're an amazing C programmer. The whole point of Perl is it's a high-level language that abstracts all the stuff you have to do in C. So you can keep your fast Perl code in Perl. You can take your slow Perl code, write it in C. And if you know how to do this stuff, then you can accomplish really cool stuff. You can also make Perl itself more useful. You can interface with libraries written in C. There are all kinds of libraries out there that are C libraries that Perl programmers may want to use. So you can create modules exposing those external APIs to Perl. And now you put that on CPAN, and now every Perl programmer who wants to use library X, which is written in C, can use it by downloading and compiling your module. You can also make Perl itself do interesting stuff. You want to change compiler opcodes on the fly. You can do that. You want to extend the parser itself. You can do that if you're crazy. You want to make exceptions work. You can do that too. There are all sorts of things. And we're not going to cover all of this stuff. We're just going to look at some really basic examples. But the point is, once you get into this area of development, your opportunities are essentially limitless. You can do basically anything. So that brings us to the two-letter boogeyman, XS. And what actually is XS? We often talk about Perl modules that are written in XS. It turns out there's a man page, as there is for just about everything in Perl. You look at Perl doc, Perl XS, and it says XS is an interface description file format used to create an extension interface. I have no idea what the hell this means. But what I did is I looked at some XS code, including from the MongoDB driver itself and other modules, and I figured out what it is in actual human language, which is XS is a specialized templating language for C. That's all it is. XS is not a programming language. XS is not a mysterious dark art. It's just templating. You know, if you work with Template Toolkit or EPL or Mason, it's the same idea, just instead of making web pages, you're making C files. So here's an example. This is some actual XS right from the MongoDB driver. And you see most of it looks like C. And this is stuff that's in a .xs file. And it's basically all C except for a few of these things, like this thing that says pre-init and init and pp code. Those are just XS template directives. But the rest of this is just C. And when you compile this, it runs through a kind of pre-compiler program that comes with Perl called xsubpp. And the result, you get, this is a chunk of it, what you get out is C code. And those template directives are just replaced by lots and lots of boilerplate, which you don't want to have to copy and paste every time you want to write some C. And so there's a pound line directive there. That's a C preprocessor directive that says what line of mongo.xs this came from, which is nice for debugging. So it expands all this stuff out for you, so you don't have to copy all of this boilerplate in your C code. And there's a lesson here about how we use nomenclature. XS is not the same thing as the Perl API. XS is just this template language. And as a shorthand, we often say this is written in XS. But what we really mean, usually, is that it's written using the Perl API in C. And the nice thing, even nicer about XS, as ugly as it is that for a lot of things, for the 90% of things that's actually easy, you don't actually have to use XS at all. And to be more precise is you don't have to know that you're using it. And the reason you don't have to know that you're using it is because we have this amazing thing called Inline C. So let me show you an example of how Inline C works. Use Inline C. I'm going to call this function called hello. I'm going to call it twice. And then that's the end of my Perl program. So that's it. And then I'm going to put this special C token here. And I'm going to write some C code right in the same file, the same PL script as my Perl. And I'm going to define this C. It's going to say void hello, which just means this is a function that returns nothing. It takes one parameter, which is a string called name, character array in C, because C doesn't really have strings. And it's just going to printf hello my name. And that's it. That's all you need to do in order to use inline C. So how does this magic actually work? It's not that complicated. Basically, it works like this. You use the inline C module. When that loads, it's going to look at the file, and it's going to do an MD5 digest of that file to see if the file has changed since the last time you ran it. If it hasn't, then all these steps are skipped. But if it has changed, then it's going to take the C code, everything after that special C token, and it's going to run it through a custom parser, which is written using the parse recdescent, recursive descent parser. That parser is really smart, and it's going to extract all kinds of interesting clues from the C code that you wrote. It's then going to create a build of that C in a temporary directory. It's going to write the XS for you, and then it's going to compile and install that all automatically. You just type perl script.pl, and all of this happens, and it makes you very happy. So that was a pretty trivial example we looked at. Let's look at how we actually make things, how we actually make Perl do stuff in C. In order to do that, we have to understand a little bit about Perl's data structures. As it turns out, pretty much all of the functions and macros that you get in the Perl API are just functions for doing things to Perl's internal data structures. So we're going to learn a little bit about these. And there's a lot of hand waving in this. It's very vague. In previous versions of this talk, I went into great detail about what the structs actually looked like and what points to what. And people told me that that wasn't actually very useful because it turns out you can just look all that stuff up. So what I've done is to reduce all that to sort of a very conceptual level so you can get started understanding this stuff. And then I'll point you to where you can look up the details if you need them. Although for most basic stuff, you actually don't need a whole lot of insight into the structures themselves. You just have to know where to look up the right function to use. So we'll start with scalars. And the scalar in Perl is represented internally by a C struct called SV. And there are a lot of different types of SVs. This is just a few of them here. Perl internally maintains a kind of hierarchy of these SV structures. SV null is undef. Whenever you have an undef, it's SV null. RV over here on the left side is a reference. PV is a string. It's called PV, stands for pointer value, because in C a string is a pointer to an array of characters. IV is an integer value. NV is a number value, which means float. And there are a few other types, which we're not going to go into. But the nice thing about this is there's this general concept of an SV, and then there are these subtypes, and we're going to see a little bit about how they work later. But what does SV itself look like? Well, it's a struct that consists of 4 words. The size of a word depends on your platform, but we'll just stick with the abstract concept of a word. The first word in the struct is this field called any, which is a pointer. And this pointer points to a more specific structure that will contain, if necessary, other metadata about this particular scalar. So that's the first field in our struct. The next one is ref count. And if you know how garbage collection works in Perl, you know that every value has a reference count associated with it. Once there are no more references, that equals 0. The garbage collector will come and free that memory. The third field has flags and a type. So assuming this is a 4-byte word, it would be 3 bytes worth of flags and a 1-byte type. There are all sorts of interesting flags that do all sorts of crazy interesting stuff. I'm not going to go into what they are because there's a lot of them. And that is the third word in our struct. And finally, there's this thing called SVU, which is not a law and order series. It's another pointer, which points to, since I think Perl 5.10 or maybe 5.8, this additional pointer was added to point directly to the actual data of the scalar. So this will point to either a number in memory or a character array or what have you. So that's the basic idea of what an SV looks like. And it's not that complicated. It's just these 4 words in a struct. And you can actually look at the code and see how these structs are defined. It's actually kind of interesting. But you don't have to know the guts of it if you don't want to. So for example, what does the simplest possible scalar look like? Well, if we have undef, then the any pointer, that's the orange field, will be null, and the type is 0. So that's it. That's undef in Perl. But that's not too interesting. We can look at some more interesting scalars. So how about strings? Well, in this case, our SV is going to look like this again, but our any pointer is going to point to another struct called an XPV. Remember I said PV stands for pointer value, which is a C string. And the type is 4. I believe that's correct. These type numbers change between Perl versions for reasons I can't discern. I think that's correct as of the current version 5.20. So the type is 4, and what happens is our SV can also be used as a more specific type called an SVPV. So through typecasting, we can kind of implement a kind of poor man's polymorphism here. So what we have is this general idea of an SV. There's a bunch of functions that operate on any kind of SV. There's a bunch of functions that operate only on SVPVs or other subtypes. And we're going to see some examples of how that works. All right. What about integers? In this case, any points to something called an XPV IV, integer value. The type is 1. Again, I think that's right. And the SV becomes an SVIV. Similarly, floats are implemented as XPV NV, and SV becomes SVNV. So I think you can see there's kind of a pattern building up. When I started looking at a lot of Perl API code and XS stuff, I saw all these SVs and NVs and AVs and HVs. What the hell is all this stuff? But there is kind of a method to the madness. The naming is largely consistent in most cases. The capitalization rules are a little weird, but there is actually a rule there. This stuff was designed by a linguist after all. So, all right, we've talked a lot about structs. Let's actually write some code. Let's use C to make something fast. So here's an example. I'm going to start a Perl program. I'm going to use Inline C. I'm going to prompt the user for a number. And then I'm going to prompt him for another number. And then I'm going to say the sum of these two numbers is this, and I'm going to call this function add. And I'm going to write this function add in C. This is probably the simplest possible C function there is. It returns an integer, it takes an int, it takes another int, and returns the sum. Doesn't get any easier than that. So if we run this in our terminal, it would look like this. It'll say, give me a number 42, give me a number 11, the sum is 53. But what happens if we experiment with this a little more? This time I'm going to give it a floating point value for the second time, and it's going to say the sum is 73. And that's not right. And if you've done any C programming before, you know, well, then if you add two integers, that's not the same as adding two floats. If you take a float and make it an integer, it's going to truncate it. So what happened here? Well, as it turns out, inline C is crazy smart, sometimes too smart for our own good. When we ran that program and compiled it through inline C parsed the C code, and it saw that this was a function that returned an integer and took two integer arguments. So it wrote the excess code for us to coerce those two scalars into integers so that C function could run. And of course, that C function could only add two integers. So how do we fix that? We want to be like Perl, where you can add any two scalars and it just works, right? So we're going to write our first real Perl API program, and we're going to add numbers. So what do we need? This is what we're going to need from the Perl API toolkit. We're going to need a function called SVIOK. This is a function that tells us if a given SV is an integer. In other words, if it is an SVIV. We're going to need SVNOK. This tells us is a given scalar a number value or a float. In other words, is a given SV an SVNV. We're going to need this function SVIV, which takes an SV and extracts the integer value. We're going to need SVNV. I think you see where this is going. Takes a scalar and extracts the actual float value, so we can work with it in C. We're going to need new SVIV, which makes a new scalar from an integer. I think you guys see the pattern. You probably know the next one is new SVNV to make a new float from a scalar. All right, so those are the tools that we're going to need. Let's look at some actual code. The Perl part is the same. We're going to call this function add, and here's how we're going to implement add. Instead of a function that returns an int and takes two integer values, this is a function that returns an SV pointer and takes two SV pointers as parameters. Now when inline C takes this, sees this, it's going to say, aha, the programmer here wants to work with any kind of SVs, so I'm not going to do any coercion. I'm just going to pass these SVs right into the function, and then we can work with them with the Perl API. So what do we actually need to do here? All right, so this looks complicated, but it's really not. What we're doing on the first line is we're saying, all right, look at A and B. If they're both integers, then we're going to do this. We're going to return a new SVIV, that is a new scalar value, which is an integer, whose value is going to be A plus B. And notice here we're in C. In C, we can't just add two SVs together. C doesn't know how to add SVs. So we have to extract the integer values from A and B and then add them. Then we use that to make a new SVIV, which we're going to return to our Perl program. Our else condition is the same thing. We're just saying if both numbers are SVNVs, which are floats, then we're going to add them exactly the same way. Extract the NVs. SVNV returns a double type in C, whereas SVIV returns an int. We can add those together in C and then return a new NV, which we construct. For any other combination, we're going to croak. We're going to say, I don't know how to handle that combination of types. But let's actually run this. Oh, by the way, croak is a Perl API function that is the equivalent of a die in Perl code. So if we actually run this, we add 42 and 11, and it says the sum is 53. We run it again. We add 53.4 and 6.54, and it says the sum is 59.94. It worked. We can now add integers or floats. If we try to add one of each, we get our fatal error. I don't know what to do. So this worked. And this example, I think, when I first worked through this made me really appreciate actually how hard Perl works to make every binary operator work with every combination of types that there are in Perl. It's a lot of work to do that. We had to do quite a bit just to get int plus int and float plus float to work. So you can imagine how much work Perl saves you over writing the equivalent C program. So now once we get this far, everything that we need to learn is basically in the Perl API man page. And this is not a man page that you want to just read through. It's really just a reference that lists basically almost all of the functions that you need to work with the Perl data structures in order. All right. So we worked with scalars. Let's do something with arrays. Now I mentioned that SV is kind of the root type of everything. And in Perl land, we're used to thinking of scalars, arrays, and hashes as completely different things. But it turns out that internally, everything, including arrays and hashes, are implemented as these kind of pseudo subtypes of SV. So an array is a type called an AV, but that's also an SV. So we go back to our original 4-word SV structure. And in this case, for an array, our any field points to a struct called xpv AV. Again, there is a pattern emerging here. And our SV becomes an AV. So what we're going to do in this next example is we're going to square some numbers. We're going to take an array of numbers, we're going to compute the squares, and we're going to return an array reference containing all those squares for the input numbers. Now, we could write a program that just returns the raw list of squares. That requires a few more operations involving the Perl stack. This way, returning a reference to an array is a little easier, which is why I chose to do it that way. So let's look at what we will need. We're going to need SVRV. So remember, an SVRV all caps is the type of SV that contains a reference. This function extracts the referred to scalar from a reference. So this is our dereferencing function. We're going to need new AV that makes new arrays. We're going to use that for our return values. We're going to need new RV that makes a new reference. We want to return a reference to our array, so we use new RV for that. We're going to need this oddly named AV fill. This does not fill an array, but rather gets you the size of the array. It's called AV fill because the field in the xpv AV struct is called fill, which contains the size of the array. I don't know why it's called that. I guess because that's how many you have when it's filled, but it's an unfortunate naming, and that's what it's called. We need AV fetch, which is a function for getting elements from an array, and we're going to need SVIOK again to check if it's an int. We're going to need SVIV to get the integer from the SV, and we're going to need AV push for pushing stuff onto an array. All right, so these are all the functions and macros that we'll need to work with arrays. So it's quite a lot of stuff, as you can see. Again, I think it makes you appreciate how much Perl does behind the scenes. But let's look at how we actually write this. Here's our Perl code. We're asking for a comma-separated list of numbers. This map block here, I'm just doing a coercion to make sure that everything we get is a number. We could do the same coercion in C, but this just saves a few lines. So this is going to make sure that Perl treats these as numbers, and then we're going to take the result, which is going to be an array reference from this function called squares. We're passing in a reference to our numbers array. Again, I'm using references here so I don't have to deal with a stack, which could be a 40-minute presentation by itself. All right, so let's look at the actual C code. First thing we're going to do is we're going to define a function called squares. And again, it returns an SV and it takes an SV. Now remember, we want to return an array reference and we want to take an array reference. Those, of course, are both scalars, which means they are SVs. We could, if we wanted to, write this signature to be more specific, but this is sort of the habit I've been into, just treating everything as generic SV. So now we'll do some declarations. We're going to create an AV. This is going to be our the dereferenced numbers array that we got in. All right. So remember, we called this. We passed a reference to an array. So we took that scalar. We ran SVRV to extract the reference value from that SV. We cast that to an AV type because SVRV doesn't really know what kind of thing it's returning. It's just returning the pointed to scalar. So the signature for SVRV is that it returns an SV. We'll cast it to an AV, and then we assign that to this AV called array. We're going to create a new AV, which is going to be our return array. This is what we're going to return to the user. We're going to create a double pointer to an SV called temp, and I'll show you what that does in a minute. We're going to get the length of an array by running this AV fill function, so we know how many elements to fetch from it. We're going to declare I, and I is going to be our iterator, and value is going to be our C value that we're going to extract. All right, so here's our loop. And it's actually pretty straightforward. We're looping from I equals 0 to the length of the array. The first line, we're saying temp equals AV fetch. We're passing the array, which is our dereferenced input array, I, which is the index that we're getting, and 1, which is a Boolean flag that I forget what it does, but it doesn't matter. And we're taking that, we're assigning it to our variable temp, which we declared as a double pointer because for some reason AV fetch returns a double pointer to SV. I don't know why. So then we're going to look at this temp variable, and we're going to just check that it's an integer. We're only going to handle integers in this example for simplicity. So if it's anything but an integer, we're going to say we can't handle this value and croak out. Otherwise, we're going to extract that integer using sviv. We put it in val. We square val. Val equals val times val. And then we use av push to push a new scalar onto our return array. But remember, we can't just push val because that's a C integer. We have to make it into an SV so Perl can understand it. So we say push new SV, this new sviv function expects to make a SV out of an integer. We pass an integer in, and we get that SV. Yes, sir?
Isn't that first SVRV going to cause a seg fault if it's not an AV?
The first SVRV,
Yeah, on numbers or numbers.
yes, if you don't do any argument checking and you pass in the wrong kind of thing, it'll blow up. So I've left out a little bit here for simplicity. We're assuming that the user did everything correctly and passed an array reference. But yes, you would want to check that. There is a function that checks, is this RV pointing to an array, or is it something else? And so we could do that check to be perfectly secure. All right, and then we're just going to return a reference to our new array. And that's our function. All right, and that's, if we run this, we say, give me some numbers. We input some numbers here, and those are the squares. So that's as easy as it is, omitting, as you mentioned, some necessary checks that might be useful. All right, so we've done things with scalars. We've done things with arrays. Let's do some stuff with hashes. And again, if scalars are SVs and arrays are AVs, hashes must be HVs, unsurprisingly. See, I told you it's not that hard to understand. So HVs, of course, are also a kind of SV. And what they look like is any points to a struct called XPV-HV. And now our SV becomes an HV. And the HV struct is actually really interesting. It's very complicated because it consists of buckets, and each bucket has a number of keys. The keys are strings, which are SVPVs. The values are generic SVs because they can be anything, and so on. So I recommend you look at that, and I'll show you where you can look that stuff up if you're interested. So we'll do a standard hash exercise, which is we'll use hashes to find unique strings. All right, so what do we need for this? We're going to need SVRV again to dereference our input hash. We're going to need new HV to make new hashes. We're going to need new RV again to make a reference to that hash. We're going to need AV fill because we're going to pass in a array reference of words to filter the uniques from. We need AV fetch to get the individual words out of the array. We're going to need SVPOK to check if all of the items in our array are strings, because strings are SVPVs because they're pointer values. We're going to need this SVPV function to extract the actual C string out of the SV. And then we're going to need HVStore to put something in the actual hash that we're going to use. So here's our Perl code. Again, it's pretty simple. We're asking for a comma-separated list of words. I don't do any coercion on this because, excuse me, since it's console input, it'll be strings by default. So we just call uniques passing in this array of words, and then it'll say the uniques are these results. for clarity, I forgot there should be a keys there on %$result, but it works anyway because the result hash we're going to make is the keys are just going to map to undef. So let's look at the C code. And here I just have it in one big slide because I got to the end of this and I was too lazy to make multiple slides. So we're going to define a function called uniques. It's going to take an SV words, which is going to be an array reference. And again, we're not actually checking the type of reference for simplicity's sake here. But we're going to assume it's an array reference. So we're going to grab it into an AV called array. We're going to create a new HV called result. We're going to create temp the same way because we're going to use it the same. We're going to get the length of the input array the same way. We're going to create our iterator variable I, as well as a character string this time called val, which will be the actual string of each element in the array. So our loop works the same way. We're going to AV fetch into temp. We're going to check svpok to make sure that this is a string and not something else. If it was something else, there are ways within C that we could coerce it to string, but I'm not going to go over them here. And then finally, we're going to say val equals svpv of this temp. Yeah?
When you called svpv nolen, you did already an svpok check, so you should really be using svpvx, not calling the coercer, which is svpv.
I did not know that. Thank you. All right. So like I said, I have no idea what the hell I'm doing. So that's a good thing to know. So
svpv will do
yeah.
All the conversions for you. It either directly looks in the struct or it calls a conversion function, and it also does an svpok test on which to do. So it's a little.
That's good to know. All right. Thank you.
The string length is redundant because svpv will give you the length of the string.
Yep. All right. Good to know. I'm going to update this. So thanks for that. So a lot of this stuff that I did initially was looking at Perl API and cargo culting stuff until it worked, without always knowing the true reason under the hood. And I learned better for a lot of this stuff. There's still a lot of holes in what I know. But this works somewhat less efficiently than it should, but it does work. And we're going to take that value and we're going to call hvStore, which just stores a result in our hash. So result is our HV, which we want to store the stuff. Val is our key. We call strlen val, but we don't actually need to do that. New SV0 is basically just going to create an undef for us. So that's the value associated with the key in the hash. So we're just mapping words to undef. And then the last one is another Boolean flag that I don't remember. We're going to return a reference to this. And the result is we input a bunch of words with a few repetitions, and we get the unique values. So we've just worked with hashes, Perl hashes in C. So those are our three basic Perl types: scalars, arrays, and hashes. There's all sorts of other interesting things in the Perl API. In particular, the most scary sounding one is this idea of magic. And as it turns out, magic is not that terrifying. It's actually pretty basic. Magic is just a linked list of function pointers attached to an SV. So what would you use that for? Well, the functions just implement custom read-write behavior for a given value. That can be a hash, an array, a scalar, whatever. So whenever we talk about magic variables in Perl, we're talking about things like %env, right, which reads and writes to your process environment table. This is magic. So when we write env equals blah, this is an assignment operation. The Perl compiler checks, is there magic on this particular hash? There is, because it's %env. So it's going to look in that linked list of functions for a write function. And by the way, there could be multiple magics on a variable if you want to. It's going to look up that function. That function is then going to take that variable and it's going to call setEnv to set the value in your environment. So this might actually sound kind of familiar. There's a way to do this exact same thing in Perl, and it's called tie. Tie is just a kind of magic. So if you've written a tie class, you've done magic. You've just done it in Perl. And in C, there's a bunch of functions that you can look up for adding and looking up magic on various types of variables. So hopefully your terror has been defeated. And I don't have time to go into an example of magic, but it's not actually that hard. So this has been a nice introduction. Where do we actually go from here? If you're interested in learning more of this stuff, the things you want to read are the man-page Perl guts. This has details on how, some vague details on how Perl data structures are organized and some functions for working with them. The big reference is Perl API. This has a list of all the functions, well, almost all the functions that you need to make Perl do stuff. There's also an excellent document, which you can find on CPAN, called Perl Guts Illustrated. This has a lot of great information about how the Perl structures work under the hood and nice diagrams of what they all look like. I believe this has just been updated. I think within the past couple days I saw a new version come through for documenting 5.20. There's also, in particular for Inline C, comes with a pod called Inline C Cookbook, which explains how to accomplish a lot of really common tasks with Inline C and makes it clear about what Inline can do. If you want to learn more about C, these are the two best books, Practical C Programming from O'Reilly and the classic K&R C. If you would like to work on the code examples that I showed you, I have them on a GitHub repository here called Perl-API-Terror. And you can feel free to clone that and improve them because I'm sure there's a few mistakes in there. So I think I have a few minutes left for questions. So if there are any questions, I will try to answer them. Yes, sir.
This is a minor comment. In
Yeah.
your DB driver code, you were using AVLen in some loop. Later in your example, you're using AVFill. Pick one and stick with it.
I will do that. Thank you. Yeah.
When you said almost, the
Yeah.
entire API, what's missing?
There's, it's hard to say what's missing because there's a lot of stuff that's internal only. There are things that have been deprecated between different Perl versions and replaced with other functions. So I had to debug something once that was affecting older Perls, and I looked it up in the docs and it wasn't there, and I realized I had to get the old version of the pod because it had been removed. So there are, I don't remember specific examples, but there are a couple of examples of things that are just missing or don't have all the options clarified. But for basic stuff, pretty much everything you need is listed in Perl API or Perl Guts. Yeah, way in the back.
Earlier you had a slide. Inline C is crazy smart.
Yeah.
Then you went into your example of how to do addition for NB or IB. I was just wondering why you couldn't redefine your earlier example to be float and let it be crazy smart for that. Automatically convert to float.
So I think you're asking why not redefine the integer version of the add function to just use floats.
Yes.
Right, all right, so if we did that, if we changed the signature to say float add and takes a couple of floats, Inline C would convert that to float. But consider the case of if you want to just add integers, they would get converted to floats unnecessarily. They might introduce precision errors. So, for an example, you could absolutely do that. For real life, you probably would not want to have Inline C just coercing everything to floats unless you're very specific that this thing takes floats. If you want to just work with general numbers, then you might as well leave it as an SV and do what Perl does, which is different addition semantics for different kinds of numbers. Yeah.
I'm curious on if you've run any performance differences on some of your examples over tens of thousands of iterations.
So have I benchmarked this? The example is no. So these are, of course, very trivial examples. I chose them because they're the same kind of examples that you would learn when learning to write Perl, squaring an array of numbers or using hashes to find uniques. So I don't make any claims that these are actually particularly fast for these operations. I just chose them because they were simple examples that people already understand, and I chose them by analogy with what you do in Perl. But I would expect that they are a little bit faster. But who knows? All right, any other questions? All right, well, thank you very much for coming. Appreciate it.